Okay, hello logic class. This is a follow-up to something that we were just talking about earlier today in class, and I'm going to go into some of the details of the claims I was making at the very end of class, and hopefully explain things a little bit better. So here we go. The claim I want to make is that the rationals do not have the least upper bound property. All right, what is the least upper bound property, and why should I care about this, and etc. etc. Well, I think this can be explained by talking about just the real numbers. Okay, so what are the real numbers? Well, you know, we have an intuitive sense of the real numbers, and that intuitive sense is kind of geometric in that there's sort of this thing called the real number line, and we think of it as being very sort of full of numbers. It's very kind of dense. All of the numbers are sort of there. And this intuitive idea is really, I think, ancient. And the idea is just that, you know, the sort of properties of numbers that we kind of care about are inherited from geometry. And so we think we understand things called, you know, lines, for example. So, all right, what's a line? Well, a line, some kind of line L, is supposed to be some kind of collection of points, and you know, even going back to ancient times when you dealt with lines, you had certain properties that lines were supposed to have. You know, so when you intersect the line or something, you know, there always is a point of intersection. So if you construct some line M, which may be taking one point on one side of line L and another point B on the other side of line L, and if you connect points A and B together to make line M, then that's going to intersect line L somewhere. Okay, so if somehow line L had like a hole in it, then, well, you wouldn't really call that a line at all, would you? That's kind of like a bunch of points, but it sort of fails to be a line. It's only some of the points of a line. So there's this kind of intuitive sense that when it comes to a line, it has all the points that you could possibly want. Okay, and so the real number line sort of inherits that sort of property that lines have. And this was about the state of the art, as far as I can tell, when it came to talking about the real numbers. And all right, when we go to start talking about the axioms for the real numbers more carefully, then that's when we start listing, okay, what are the most sort of basic properties of the real numbers that they're supposed to have, so that I can use these properties as justifications for the various steps in my proofs when I'm doing my calculus theorems. And okay, this is just sort of a repeat of what we said in class, but the idea is that the real numbers are a field, and there are these two binary operations, you know, addition and multiplication, and there are all these things, you know, so such that if you add any two real numbers, that you get a real number, and when you multiply any two real numbers, you get a real number. And addition is associative, and also that multiplication is associative, and etc. Terminating with the distributive property. Well, okay, so multiplication is addition, associative, commutative, addition's commutative, multiplication's commutative. You have the fact that there's an identity element for addition, we call it 0, and an identity element for multiplication, we call it 1. There are additive inverses for every number, and every number but 0 has a multiplicative inverse, and then the distributive property. Okay, but as I said, this is just all a repeat from class. As I said in class, and maybe we shouldn't even spend any more time on this. As I said in class, when it comes to listing all these properties that real numbers have, well, the rational numbers have all these properties too. If you add two rationals, you get another rational. If you multiply two rationals, you get another rational. That for every rational number, you know, they satisfy the associative property, the commutative property, the distributive property, etc. So there must be something different. You know, real numbers have some kind of extra fact about them that the rationals don't. And okay, this is just exactly the thing I was saying in class, that what sort of property does the rational number line have? Well, you might say that the rational number line is not a line at all. It's just a kind of a collection of points because it fails that sort of intuitive line property that we were talking about, which is that if you go to the point on the rational number line where root 2 is supposed to be, well, it's not there. So you can prove that the square root of 2 is irrational, and so were some line to kind of intersect, there would be kind of no point of intersection or something. So the rational number line kind of fails this kind of line property. All right, so that's kind of fine, I guess. But if the goal is to axiomatize the real numbers, and by that I mean definitively list out all of their properties, then clearly the field axioms are insufficient because both the rationals and the reals satisfy the field axioms. So besides just telling me that root 2 is not rational, I need to know what extra property do the real numbers have that the rationals don't. Okay, and there's maybe a longer story that goes into how people came up with this idea. I guess I'll leave this picture up, but I'll just say the answer. The answer is that the real numbers have this extra property called completeness. Okay, I don't like to use this word because I feel like this word completeness is overused. So I'll say it now though because that is what people call it. And what do people mean when they say the real numbers are complete? They mean they're all there. So they behave in this same way that lines behave in. That if you intersect them, you always actually hit a point. There are no gaps. There are no holes. Okay, but of course the whole idea is that we are moving towards basing calculus on real numbers. And not on geometry. So we do not want a geometric basis. We want some kind of independent, non-geometric formalization of this property, which is intuitively geometric. But we don't want to lean on the geometry. Okay, well, that's when you introduce the least upper bound axiom. And the least upper bound axiom is an axiom which provides this extra property that the real numbers have that the rationals don't. And what the least upper bound axiom says, the least upper bound axiom says that for any subset S of R, if S is not empty and S is bounded above, then S has a least upper bound, which is a real number. Okay. And what does this kind of mean? This axiom you can think of as kind of guaranteeing that wherever you go looking on the real number line, that there really is a real number there. And I don't think I sort of was stumbling over my words, unfortunately, today in class, and I don't think I said the exact right things in the exact right kind of spots. But just to kind of repeat what happened today in class, we considered this set of real numbers between 0 and root 2. And if you look at all the real numbers between 0 and root 2, then you can consider, so call this set S, the set of all numbers which when squared are less than 2. And for all of the numbers which are upper bounds, that's what it means to be a least upper bound. It means you're an upper bound and you're less than any other upper bound. So here I shall add several blue dots indicating numbers which are upper bounds for this set S. Each of these blue numbers that I mentioned is greater than all of the elements of S. However, there is one number which is the least upper bound. And the least upper bound of this set S is the number root 2 itself. And so by postulating that given any set of numbers, there is always a least number, which is bigger than every number in that set, kind of guarantees the existence of a real number anywhere you go looking for it. That's one kind of informal way of putting it. If you have some spot on the real number line and you want to know if there's a real number there, well, there is. Okay, good. So I think this is the simplest and most straightforward way to talk about the least upper bound axiom, is as just an axiom of real numbers. So if you give me any subset of real numbers which is not empty and which is bounded above, in other words there exists an upper bound, then there is a least upper bound, and that least upper bound is a real number. Now, more abstractly, and I wish I had done this kind of second, you can discuss the least upper bound property. So what is the least upper bound property? Well, it's a property that a sort of ordered set of numbers can either have or not have. And okay, so now more abstractly, kind of some ordered, you might even say totally ordered, set X has the least upper bound property, if and only if. Now I just restate everything I said here, but now sort of abstractly in terms of this set X. Okay, so what does it take for some set X to have? Think of X as a kind of number. So X is either like the real numbers or the rational numbers. So some ordered set X has least upper bound property if and only if. Well, it's just this again, right? For any subset S of X, which is non-empty and bounded above, then the least upper, then maybe it's best to say, then S has a least upper bound, and crucially in X, which by that we mean that the least upper bound of that set should be one of the elements of this set X. Okay, so hopefully this is clarifying things a little bit. It's kind of just patching up what happened today in class. Possibly this is just a repeat. The real numbers have the least upper bound property. In fact, the least upper bound axiom of the real numbers is just the statement that they have the least upper bound property. But I claim the rationals do not have the least upper bound property. And the best way to see that the rationals do not have the least upper bound property is to consider the rational real number line. And if you look at all of the rationals in between 0 and root 2, then so here is a set of here's a set of rational numbers. So I'm going to just kind of color this red. I'll call this set S. And if we consider this set, which by the way we can write it out precisely, what is this set S? It's the set of all X, such that X is rational, and X squared is less than root 2. And let's just have X be positive as well. Okay, sorry, X squared is greater than 2. Okay, so this is kind of preferable because now by I'm sort of avoiding the mention of the number square root of 2 at all, and making it sort of just a pure statement about rational numbers. Consider the rational numbers which when squared are less than. Consider the positive rational numbers which when squared are less than 2. Okay, and this is supposed to be an example. So this set S is just exactly what we did in class. This set S is non-empty. It's bounded above. So this is what I said, right? 1 is in S, so S is not empty. And for all X, if X is in S, then X is less than, say, 5. So that's just another way of saying 5 is an upper bound. So this set S is a non-empty set of rational numbers which is bounded above. But unlike the real numbers, this set S has no least upper bound. S has no least upper bound. Okay, and so I'm kind of explaining the least upper bound axiom for the real numbers by showing that the rational numbers do not meet this axiom. So, or the rational numbers do not have the least upper bound property, whereas the real numbers do. And by showing how the rational numbers fail to have the least upper bound property, we supposedly understand the least upper bound property better, and we see that it's something that the real numbers have. So the idea here is kind of a contrast. Okay, why do the rationals fail the least upper bound property? Because here's a subset, and this subset does not have a least upper bound. In other words, contrary to the real numbers, when you go looking for, it's not quite the biggest number of the set, because the biggest number of the set might be in the set or it might not be. It's kind of the smallest number which is bigger than every number in that set. In fact, that's exactly what it is. That's the definition of a least upper bound. It's the least number which is an upper bound. So of all the numbers, and once again, I will draw a bunch of blue dots. These are now rational numbers under consideration. Each of these rational blue dots here is greater than all of the rational numbers in this set S. But, whereas in the case of the real numbers, there is always a least one among those blue dots. It's that green one. Here there is no least one. And so there really is, in a certain sense, numbers kind of missing from the rational number line. The power of the least upper bound axiom is that it gives me sort of the ability to kind of posit that there is always a number there. Whereas with the rationals, I can't make that statement because it's just false. Right? There is no one. Okay, so that was pretty good, and I think the average person could just stop watching now. Hopefully, for those of you who totally got it, this was just a recap. For those of you who found it confusing, this was just a more carefully and slowly explained explanation. Perhaps keep watching for 1 or 2 more minutes, because I'd like to do something now which no one ever does, which is to actually justify this claim. The claim is that there is no least upper bound. So, for this set S. So now let me kind of erase all this, because this is the goal of this entire video, is to execute this proof that is quite involved, actually. And so once again, I shall introduce this set S. What is this set S? It's a set of rational numbers. And actually, perhaps it's just kind of more succinct to write Q plus. So consider the set of positive, this just means positive rationals. So, consider the set of positive rationals such that x squared is less than 2. And now I am going to make a claim, and the claim is S has no least upper bound. Okay, and I want this to be understood properly as a theorem about rational numbers. Maybe I'll even just write that up here, right? This is a theorem about rationals. And so, I am not going to mention ever again, kind of on this board, anything about irrational numbers. In fact, you could very well not even believe in the existence of irrational numbers, and everything I'm about to say still holds. Okay, so imagine a world of just rational numbers. Well, I'm going to prove to you a fact about rational numbers, and here is the fact. The fact is that there is no least number which is bigger than all the numbers which when squared are less than 2. Okay. More casually, I want to say there is no least rational number which is bigger than root 2. But I want to sort of avoid actually writing root 2 on the board. So what does it mean to say that S has no least upper bound? Well, what I mean by that is for any upper bound, of S, let's call it, let's see, how I did this on my paper, I said call it Q. There is a smaller upper bound. There is a smaller upper bound. Okay, so this is the claim, and okay, so the picture is kind of like this. The picture is that there's this rational number line. I redraw the picture now, sort of one more time. So I won't write root 2 on my paper because that's contrary to the spirit of things. But here are all of the rational numbers which are positive and when squared are less than 2. And okay, now considering some upper bound Q, what I must show you to convince you that this is all true, I must construct a smaller upper bound. And because this can be done for any upper bound Q, that there's always a smaller upper bound, then this is literally what we mean when we say this set has no least upper bound. Okay. Alright, and maybe even just because we will do it with, write this out one more time and kind of quantify our logic. So just so that no one could possibly misunderstand, here's the statement. For any Q such that Q is rational, one second. I guess this is actually slightly wrong on my paper. For any Q, if Q is rational, then, I want to say, yeah, oh man, sure, no, it was fine the way it was, okay, for any Q, if Q is rational, and Q is an upper bound for this set, which by that we mean that for all x, if x is in S, then x is less than Q, close the parentheses again, then, so what's x? X is just some arbitrary element of this set S. Yeah. Cha-cha-cha. So if Q is a rational number which is an upper bound for this set, it's bigger than every element in the set, then there exists another number P, then there exists a P such that P itself is also rational, and P is an upper bound, gotta write small now, for all x, if x is in S, then x is less than P, and P is less than Q. And now close that and close the whole thing. Okay, so this might help some people. This is just an extreme level of detail, totally unambiguous statement in quantifier logic of what we mean. Okay, if I can prove this, then I will have shown you that this particular subset of the rationals has no least upper bound, and therefore that more generally the rationals do not have the least upper bound property. Alright, so what's the goal? The goal is that you need to construct a P. So the goal is like for any Q with Q squared less than 2, the goal is to construct P such that P squared is still bigger than 2, but that P squared is less than Q squared. Of course, if P squared is less than Q squared and P and Q are positive, then P is less than Q. So okay, this should be the whole, this is the whole argument right here. I'm going to show you how you give me a rational number Q, which when squared, sorry, that's wrong. Q squared should be greater than 2. You give me any rational number Q, which when squared is bigger than 2, in other words, Q is an upper bound for this set S, and I am going to show you how to, I'm going to give you a P such that it's an upper bound for this set because p squared is greater than 2, but that p is less than q. Okay, that was a long build-up, and now we're kind of ready to just do it. Unfortunately, I need like so much more board space, so I might just now erase this entire thing, and so I can have all the board space and count on my audience to either take a screenshot of this or just kind of get it enough that we don't need any of this anymore. But this is the big picture. Okay, so good. Okay, and I did this proof myself, so that's kind of exciting. I'll kind of explain how I came up with it as well, because it's no point in just giving the proof if you just think of it as just a bunch of things coming out of nowhere. I'll rewrite the goal again. The goal again is to produce a P which is less than Q, but still an upper bound. Okay, right. What are we going to do? I have no idea how to do this, but I am a, very good high school math teacher, and so I have some strategies which I have used to do various induction problems and epsilon delta proofs and things like that. So keeping this all in the world of rational numbers, this was my thought process. I said, okay, I'm not positive this is going to work, but it feels like it should. Let P be Q minus a little bit, where for some n natural number. In other words, let me just define P as sort of just construct P as a number which is less than Q. And now let's just figure out how big n needs to be in order for this to be true. Okay, and so working backwards, what I need to be true is I need it to be true that P squared is greater than 2. And so basically I've defined P, or rather I've defined P such that it is guaranteed to be less than Q. What is P? P is a number which must be less than Q and also when squared bigger than 2. So I define P as less than Q, and now I'm going to figure out what does n need to be so that P squared is greater than 2. Yeah, I think that's pretty clear. Okay, well, then what that really means is Q minus 1 over n squared needs to be greater than 2. Okay, now just comes a whole bunch of little bit of algebra. So okay, let's get a common denominator in there. Qn minus n over n squared has to be greater than 2. I might need to write smaller. Okay, what now? Just let's do stuff, right? So this is like Q squared n squared minus 2, wait, what? Oh yeah, multiply both sides by n squared is what I'm doing. So I think this is just wrong. This should be a 1. There we go. Q n minus 1 over n. Okay, so Q squared n squared minus 2 Qn minus 1 has to be greater than 2n squared. What are we doing again? We are working backwards to figure out what n needs to be in order that P squared be greater than 2. So I am basically going to reverse my steps to find the n that makes this true, and I'm going to pursue sort of reversible steps all the way. By the way, I should have mentioned 5 minutes ago that if you're not interested in this problem, this is a good time to turn this video off and feel like you just get it. But for those who are interested in the details, here are the details. This should be a +1, of course. Okay, whew, man, algebra. Okay, let's just express this now as a function of n. So this is Q squared n squared. Bring that over to the other side. So this is Q squared minus 2 is the coefficient of n squared. Minus 2qn plus 1 needs to be greater than 0. And, okay, looking good. let's divide by q squared minus 2. So n squared minus 2q over q squared minus 2, n plus 1 over q squared minus 2 needs to be greater than 0. So I have now like a quadratic in n, and well, what are we going to do? We're going to complete the square, of course. So let's see. This needs to be n squared minus 2q over q squared minus 2 n, and so I'll put in greater than 0. That's negative 1 over q squared minus 2. And now I need to add something to both sides to complete the square. And the thing to add is, well, it's just half of that squared. So I add q over q squared minus 2 squared. And I add q over q squared minus 2 squared to the other side as well. This is looking pretty terrible. Does this get any kind of better? Yeah, I guess. This whole left side now becomes, oh boy, it becomes n minus q over q squared minus 2 quantity squared is greater than, well, when I get a common denominator here, I get q, so I need to multiply this by q squared minus 2 over q squared minus 2. So that's like 2 minus q squared, but then there's a plus q squared over q squared minus 2 squared. So in fact, this whole thing is just 2 over q squared minus 2 squared. Okay, and great. Well, I'm now ready to kind of pause or something, and so what do I need to be true? I need it to be true. I need the n to have the following property. I need n to have the property that n minus q over q squared minus 2 squared is greater than 2 over q squared minus 2 quantity squared. So what thing should be true about n in order for this to be true? Well, okay, what I decided is that because I kind of want to take the square root of both sides now, but I need to keep everything in the land of rational numbers. So if I need this to be bigger than 2 over q squared minus 2, why don't I just say that it's bigger than 4 over q squared minus 2 squared? Because if it's bigger than 4, then it is automatically bigger than 2. And having done that, then it suffices, maybe need is now an exaggeration, but it suffices for what I'm trying to do, for, now I take the square root of both sides, for n minus q over q squared minus 2 to be bigger than 2 over q squared minus 2. And thus, oh, and actually greater than or equal to now is sufficient, right? Because I need to be bigger than 2, but 4 is bigger than 2. Okay, so I need this to be true, and now finally, I hope this is the final step. Yeah, I now just add them both. And so my end goal is if I just let n be bigger than q plus 2 over q squared minus 2, then everything is going to work out. Okay, so this is like the discovery phase. What I think now suffices is if I just set n to be, if I just set n to be that number. In other words, what have I really done? I have expressed n as a function of q. So what is q? Q is the upper bound. Q is the number the rational number which when squared is bigger than 2. And n is a tiny, n is a very, very large number. And in fact, if you look down here, you can see that the closer q is to root 2, so the closer, the smaller of an upper bound q is, that means that q squared will be just a tiny bit bigger than 2. In other words, that denominator becomes very small, and this fraction becomes very big. So the closer q is to root 2, the bigger n has to be. And what is n? It's kind of a measurement of how, well, the bigger n, then the tinier the gap between p and q is, or something like that. Okay, let's just now just kind of do the proof. So here's the proof. Here's the forward direction of the proof. It's actually much simpler than the backwards direction, I think. So here's the forward direction. So I'll just take it from the top, right? Take some q, which is a positive rational number, such that q squared is greater than 2. I now know that this is what I have to do to make this proof work. Take a new rational number, p, which is q minus 1 over n, where n has been defined to be q plus 2 over q squared minus 2. Okay, and lurking in the background here are some properties of rational numbers, which is that if q is rational, q squared is rational, q squared minus 2 is rational, that numerator q plus 2 is also rational, so n is a rational number. If n is a rational number, then 1 over n is rational, q minus that number is also rational. So p, by construction, only performs kind of rational arithmetic on rational numbers. So p is guaranteed to be rational itself. And so I'll just state that. Not only is p rational, but also, let's see, what do I want to say? Okay, so some more sort of preliminary comments. So since q is positive, oh, this is like maybe too much detail, but since q is positive, you know q plus 2 is positive, that is to say the numerator is positive of n, and also, let's not forget that that the by definition q squared is greater than 2. So since q squared is greater than 2, then the denominator q squared minus 2 is also positive. So if the numerator and denominator of n is positive, then that means that n is positive. And if n is positive, then p, which is q minus something positive, then p is indeed less than q. Okay, great. And if p, and that's the entire point, right? The entire point is to find a rational number which is an upper bound, but which is less than any given upper bound, the given upper bound q. Okay, so now comes my final claim. My claim is that clearly this number p is less than q, but what the real thing I need to show is that it is an upper bound. So the only thing left to do is show that p squared is bigger than 2. If p squared is bigger than 2, then I'm done, because I found this upper bound, which is less than q. Okay, good. How do we prove it? Well, we begin. Yeah. So just take, this is how I did it, I guess. Take q, so just take p squared. What is p squared? It's, p by definition is q minus 1 over n. So take q minus 1 over n squared. Well, what is that actually? It's q minus 1 over that whole thing. So 1 over that would be q squared minus 2 over q plus 2. That whole thing squared. And that turns out to be, what is this? Q squared plus 2q minus q squared plus 2 over q plus 2. That whole thing is being squared. And so this is, in fact, just 2 q plus 1 over q plus 2 squared. Okay, so this is the thing that I must show is bigger than 2. Why is this bigger than 2? Well, now I will, that was kind of a bunch of algebra simplification, so now here's kind of my statement. My statement is that's 2 q plus 1 over q plus 2 quantity squared is greater than 2, kind of if and only if, and now I claim that I pursue equivalence preserving kind of operations only. So multiply both sides by q plus 2 squared, and this is going to give me 2 times q plus 1, that whole thing squared, and this is 2 q plus 2 squared. Okay, so what is all this crap? This is like 4, q squared plus 2q plus 1, and this is, so again, just algebra, if throw in the if and only if, 2q squared plus 2q plus 4, so that's 4 q squared plus 8q plus 4, 2q squared plus 4q plus 8. I hope this is just right. Geez. Oh, wait, I could have just canceled. Sorry, should have done that. Cancel. Well, okay, maybe. Sorry, I wasn't really thinking about what I was doing. I should take a 2 out of both sides. That's the better thing to do. So this becomes 2q squared plus 4q plus 2 is greater than q squared plus 2q plus 4. Okay, so what do we get? We get q squared plus 2q has to be... What have I done? It's possible I just made some horrible... Oh, that should be a 4. Oh my god, bad algebra. Okay, I think this is all good now. I'm just making a lot of mistakes. This is legit. This is legit. I divided both sides by 2. I distributed that 2 through. Here I square q plus 2 properly now. And so this whole thing now boils down to q squared is bigger than 2. And that's just true. Okay, so the proof turns out to be, kind of very simple, actually. The hard part, as usual, was the kind of discovery phase. If q squared is bigger than 2, which it is, then we may go from this line up to this line by just like adding some terms, factoring, kind of factoring some more, and doing this, and that just is p. So, alright, I claim this whole thing is done, that I have, in fact, constructed this rational number, p, and I have constructed it in such a way that for any q you choose, p is a lower upper bound. Thus, there is no rational least upper bound for the set of rational numbers less than root 2, contrary to the real numbers, which do have this property.